All right. Well, officially, good afternoon, everybody. Welcome back to day 8 of Intro Physics. Um, so yesterday we wrapped up kind of our crash course in calculus. So derivatives and integrals, how we can do that mathematically, also how we can do that graphically if we're given those position time, velocity time, or acceleration time graphs, how all of those things are related to each other. Remember, tomorrow I will be posting the answer keys to all of those practice worksheets that are posted on Canvas. So if you haven't had a chance to look through them yet, make sure you do so at some point, and then you can check out the answer keys starting tomorrow. Today, we are moving into a new sort of topic. I say sort of new topic because it is a familiar topic. We're just kind of expanding it now. So not just motion in one dimension or motion in a straight line, but now motion in 2 or 3 dimensions. That's sort of what we're going to be talking about for the next few days. So let me go ahead and share my slides with you. All right, can we all see our chapter 2 and 3? Thank you, Victor. I can always count on your head. Okay, so here we go. Motion in 1, 2, or 3 dimensions, how we can take the things that we learned the past few days and extend that into, I guess, a more advanced setting. So we had just been talking about derivatives for the past few days, and yes, they are actually applicable to things that we will talk about in the future.
Hello, Miss Zamora.
Hello. Yes, go ahead.
My apologies for just interrupting like this, but I do have one question. It was about the lesson from 2 days before. Are we gonna continue on, or should we do that by ourselves?
You mean the derivatives that we were talking about together?
Yeah.
Yeah, so I had posted like the remainder of that lesson, links to videos on that. I posted that yesterday. So hopefully you have access to those.
I was not able to look at the videos yesterday.
Okay, well, take a look at them over the weekend, and if you have questions, let me know, and I'd be happy to go through it with you.
Okay.
So we're going to put some of the things that we had just been talking about into practice as we go through these equations. So we're going to start with this equation. X equals beta, another Greek letter, t, plus 1/2 gamma t squared. Okay, so that's our equation that we are looking at. Now, if we want to take the first derivative of this equation with respect to t, remember that notation would be dx over dt. So x tells us about the function that we're interested in, that equation x equals. And then the variable that's in the denominator, that t, tells us the variable that we are going to take the derivative with respect to. So dx dt means take the derivative of equation x with respect to the variable t. Yeah, we don't want to disrespect t here. Absolutely right. So when we take the derivative of a position equation, that gives us a velocity. And so when we do that, we can apply the power rule like we've been talking about previously, right? So that first chunk of the equation, beta times t, if we take the derivative of that using the power rule, we'll get the coefficient beta times the exponent on t, which is 1. And then we subtract 1 from the exponent on t, which makes the exponent 0. T to the 0 is 1, so beta times 1 is beta. That second chunk of the equation, 1/2 gamma t squared, if we apply the power rule to that section, then we multiply the coefficient by that exponent. So 1/2 gamma times 2 is just gamma, right? 2 over 2 is the same thing as 1. It simplifies to 1. So we get gamma, and then we subtract 1 from the exponent squared, and we get t to the first. Yeah, so a question in the chat, what does beta stand for? Like what value? So there is an answer in the chat, initial velocity. Yes, it does. In this case, I'm just using beta just to keep it kind of like general since we're just looking at derivatives right now. But yeah, if we want to apply this to actual physical quantities and physical terms, that would be our initial velocity. Okay, so if we take the second derivative of that function, that initial function, then that's the derivative of v with respect to t. So dv dt is one way that we can write it. We could also write it x double prime, right, with 2 apostrophes, or we could write d squared x dt squared. That's another notation that we could use. Either way, we're talking about the acceleration here. And so when we apply the power rule to our equation for velocity, v equals beta plus gamma t, beta is a constant because it's not the variable that we're interested in, right? We're interested in the variable t because that's what's in the denominator of our derivative expression here. So that will go away because the derivative of a constant is 0. And we're left with just gamma once we take the derivative. So that's our acceleration. So that means that we can replace gamma with a, acceleration, wherever we see it in any of the equations. So in that first derivative equation, beta plus gamma t becomes beta plus at. And if we know that acceleration is the change in velocity over a change in time, then a times t is the change in velocity, right? So by v, we really mean the final velocity. That's what that variable in our equation is referring to. So that means that beta must be our initial velocity. And so our equations, if we actually go through and plug in all of our variables that we've just found, our equations become x equals vi, initial velocity, times time, because remember beta is initial velocity, plus 1/2 at squared. And then our first derivative becomes final velocity equals initial velocity plus a t squared. Remember, a is acceleration and t is time. And then
I'm a little confused.
Yes, what's your question?
How did we get beta to be final? Not final, but initial velocity.
So if v in our equation here means the final velocity or the velocity at a particular instant that we're looking at, and we know that acceleration is the change in velocity divided by the change in time. Remember, the change in velocity is the same thing as v final minus v initial. Okay, so basically just algebra here. Once you plug in those things that we know, right? V is v final. Acceleration times time is our change in the velocity. That means the change in velocity plus the initial velocity gives us our final velocity. Right? Or if we move the beta over to the other side of the equal sign, then we would end up with v final minus beta equals change in velocity v final minus v initial. So if we have v final minus beta equals v final minus v initial, and those two things have to be equal to each other, that means beta has to be initial velocity. Does that make sense?
I'm sorry. No.
Okay. Let me grab a piece of paper real quick so I can actually write it out for you. I'm going to stop the recording for just a moment. Okay, and we're back. So, hold on one second. Okay. So V equals, okay, so here's our equation. This is a really terrible equal sign. Equals, V equals beta plus AT. Okay. Now, if we assume that V equals our final velocity, or velocity at a certain time that we're interested in. We can plug that in to our equation, right? So we just made v our final velocity.
Okay.
Okay. So we know from the definition of acceleration that it's delta v over delta t. And when we take delta as something, that's the final minus the initial. Right there. Okay. So that means that acceleration times time, or times change in time, is final velocity minus initial velocity.
Wait, hold up. Can you hold it up for a little bit?
So we just took the denominator here and multiplied it on both sides. So a times change in change in time equals final velocity minus initial velocity. So I was just algebra moving this variable over to the other side of the equals.
How come we move the t to the other side?
Because when we simplify equations, whatever we do on one side of the equation, we can do to the other side as well, and it will remain equivalent, right? So if we want to get the numerator by itself, then to undo this delta t in the bottom of the fraction, we would multiply the whole fraction times delta t. Sorry, it's getting kind of squished here. But if we do that on this side of the equation to cancel out, right? When you have something on the top and on the bottom, you can cancel it out. If we do that, we also have to write that on the other side too. So we multiply both sides of the equation by delta t. That way we can cancel it out on this side of the equal sign, and we're left with just vf minus vi equals a times delta t, is what we have here. So these two equations are equivalent to each other, right? Because if we were to undo it, for example, if we just divide both sides by delta t, then we'd be back at the same equation that we started with. Okay, so now if we know that v final equals beta plus AAT, then we can plug in this chunk that we just kind of messed around with. Okay, so v final equals beta plus, now we're substituting in AT to be v final minus v initial. Okay, so now I'm going to simplify that equation a little bit more. V final minus beta equals v final minus v initial. Right, so I'm just taking the beta and moving it over to the other side of the equal sign. Since it's added here, that means I subtract it over here. And if we compare these two parts of the equation, right, v final minus beta equals v final minus vi, the only way that can be true is if beta equals initial velocity. Okay, does that make sense? Seeing it written out?
Yes.
Okay.
I was just getting a little, I guess I just got tripped off because we were using like Greek letters, not Greek, but like, yeah, Greek letters in place for the actual variables. And that started to like kind of just trip me up, and like I couldn't, that's where I got lost.
Yeah, and that is absolutely valid. However, that is something that you'll have to get used to, because as you go into college physics, professors are going to expect you to know where these equations came from and be able to derive them yourself. So be able to go from like just your x equals whatever equation. And if you happen to not write all of the equations down on your equation sheet for a test, they're going to tell you, too bad, figure it out, derive it.
But wait, no, just like confused because uh, like it's really confusing. Like they look familiar if I replace them out, but like it's confusing because then I just think it's another equation entirely for another thing.
I know, and your confusion is valid, but it's something that you just have to get used to, unfortunately. Um, because different professors, different textbooks will use different variables to mean the same thing. There's really not, like in some cases, there's really not consistency from like old textbooks to new textbooks. They'll just be like, oh, well, I think this variable makes more sense here, so I'll put in, this variable instead of the old one that we used to use. Um, so if the equation looks sort of familiar, then that's really what the important part is, because it's not going to be written exactly the same way for every professor and every textbook that you'll ever see it as, unfortunately. So again, your confusion is valid. And this is why I'm presenting it in a lot of different ways, because I don't know which professor you'll have. I don't know which textbook they will use. So I want you to be familiar with looking at an equation and saying, hey, like, how can I make this, like, does this match something that I already know? It's just a skill we got to learn. Okay.
Hmm. I feel like I would have much more easier time if I was just dealing with numbers instead of using the numbers like applying the numbers to real life situations.
Yep. But unfortunately, you'll find the farther you go in math, the less numbers there are. So that's unfortunate. Yeah, math becomes much more variable based than number based. So it's just an introduction to it. Okay. So these two equations that I have in the bottom, these yellow boxes, these are the more common ways that you'll see them written. But again, these are not the only ways that you might see them written. Different variables could be used. But these equations are called the kinematic equations because they're equations that deal with motion. Kinematic means motion. Okay, so physics is more than just a bunch of equations. However, like as you create equation sheets for tests, you might feel like, man, physics is just a bunch of equations. But those equations have meaning. They, express the physical world in a way that we can kind of visualize and simplify a little bit. So equations are pretty cool. They're helpful, and it is helpful to know where they come from. But here are what I refer to from here on out as the kinematic equations. So there are a lot of different equations that pertain to motion that will be used throughout this class and Physics 1 and beyond. And these equations work in both the X and the Y directions, as long as you keep those directions separately. So if you're dealing with horizontal motion, typically you'll use the variable X for horizontal motion. If you're dealing with vertical motion, you'll use the variable Y most often. And these equations still hold for any kind of like constant velocity, constant acceleration type of situation, right? These equations still apply. But if we have multiple directions at the same time, so if things are moving both horizontally and vertically at the same time, then we have to think about those two motions sort of separately. Okay. Also, if we take a look at some of these like chunks of equations, for example, this one here, delta x equals 1/2 vi plus vf times t times time. That 1/2 vi plus vf is just the definition of average velocity, right? If you take the average of something, you add the things together and divide by how many things you have. That's how we take an average. So when we're taking an average velocity, if we have two velocity measurements, we add them together, divide by 2, that's our average velocity. So this equation, delta x equals v average times time. That's an equation that we mentioned like last week for motion in one dimension. And even just the definition of average velocity. Okay. So my recommendation to you, these equations, you will use them a lot. So if you can memorize equations, these are good ones to memorize. If not, I highly recommend that you have them written down on an equation sheet somewhere. Even like as we go through examples together, have these written down somewhere so that you can easily refer back to them. Now, for at least some of the examples that we do, I will have them all kind of in a box in the corner for you to refer back to. But again, these are the kind of the bread and butter equations. These are the foundational equations for motion.
It stands for F is for final and I is for initial, the start.
Yes. However, for initial velocity, you might see that written as v sub I or v sub 0, because we're saying like at time equals 0. So at the beginning, what is the velocity? So another way for VF, again, you might see that just written as V. So that's our final or the current velocity that we're interested in. Like I said, different books, different professors will kind of use different subscripts or different variables for the same thing. So there's a question in the chat. What does V2F and V2I stand for? I'm assuming that you're talking about this last equation. And this is just the final velocity squared equals initial velocity squared plus 2 times acceleration times our change in position. Okay. You're welcome. So these two equations we had seen previously, right? Our definition of average velocity and average acceleration, those should look familiar. This one we just derived on the last slide. Like I said, this chunk, meaning average velocity, is kind of a rearrangement of this first equation. Okay, we derived this one on the previous slide as well. Okay, so this is really the only like brand new one to us at the moment. We've seen all of the other ones, or we can arrive at all of the other ones kind of, they're connected. Okay. So we're going to do an example using these equations, and I have them numbered off to the side now, just so I can really quickly refer to like equation 6 or equation 3 or, you know, whatever equation we're using. So a car starts from rest and accelerates at a constant rate of 5 meters per second squared. Okay, so there are a couple of key bits of information here just in that problem statement itself that we're going to want to make note of as we go through these problems. So I always recommend, first of all, drawing a picture, right? I've said that before. If you can draw a picture, it's very helpful. But I also want to recommend that you make note of any numbers that you might be given in the problem statement, or any bits of information, even if they're not numbers, that might be hints at something. For example, the car starts from rest. Okay, that's not an actual number, so your eyes might just kind of skip over that when you're reading. But from rest is a really important phrase to pull out.
It means that it started from 0.
Exactly. Well, what is 0?
The car.
What about the car?
It's resting.
Okay, but what is equal to 0 when the car is at rest?
It's velocity.
It's velocity, right?
Yo, I was about to answer that.
Is 0.
And acceleration, maybe?
Well, I mean, yeah. So if we
Comes with the
look
territory.
at- yeah, later in the problem statement, the acceleration is constant. That's important to know. Right? It's a constant acceleration of 5 meters per second squared. That's a positive number. So we know about the motion of the car by looking at the signs of the things that were given. Okay, so we know a lot of important information just from the problem statement itself. So get used to reading these statements very carefully. And like I said, maybe off to the side of the problem somewhere, start jotting down the variables that you are given. So from the problem statement, we know that VI, initial velocity, equals 0, and A equals +5 meters per second squared. Okay. So if we want to know part A, what is the velocity of the car after it has traveled 30 meters? Now we want to start thinking about, all right, what am I looking for? We know some things that we were given. What am I looking for? We're trying to, if we think through that like IC problem solving strategy, right now we're identifying the variables and we're setting up the problem. Now, based on what we're looking for and what we're given, those variables will help us determine which equation we should use for each different question. Because you'll see that these equations, a lot of them have like common variables. So for example, equation 3, equation 4, equation 5, 6, they all have initial velocity like expressly written out. And then equation 2 also has initial velocity kind of hidden inside of it. So if we're given the initial velocity, that's great, but like that in itself doesn't really help us narrow down which equation to use. Now we know that we're also looking for the final velocity, right? The velocity of the car after it has traveled 30 meters. So now we need to make sure we're using an equation that also has final velocity in it, since that's what we're looking for.
Oh, can I suggest an equation?
Sure.
How about 3?
Ooh, equation 3, let's take a look. So it has final velocity, that's good, we need that. It has initial velocity, that's good because we have that. It has acceleration, that's great because we have that. And it has time. Well, we don't really know anything about time yet. So if we're trying to figure out which one might be best to use, number 3 could be helpful later on if we find time first. But if we look at equation 3, it actually has 2 variables that we don't know anything about, right? Because we don't know the final velocity and we don't know time. So let's see if there's another one that might be more beneficial based on what we are given.
How about number 6?
Yeah, number 6.
Okay, so we have a couple of suggestions. We have a suggestion. Okay, yeah, number 6. So the final velocity, right? That's what we're looking for. Initial velocity, that's what we have. We have acceleration, delta x, right? That's our change in position. If we look at this statement of part A, it says after it has traveled 30 meters, right? So we know that it's changed its position by 30 meters. So that means we have delta x. So number 6 would be a great equation to use for part A because it has all the things that we need and the things that we are given. Cool. Okay. So if we take equation 6 and I just simplified it for you, I got rid of the square root. I'm sorry, I got rid of the square on final velocity by taking the square root. So we plug in what we're given, right? From rest means an initial velocity of 0. 2 times our acceleration of 5 times our change in position of 30. That gives us a final velocity of 17.3 meters per second. All right. So let's just think through B really quickly as well. How much time has elapsed? So what variable are we looking for in this case?
T.
T, yes, T. Good. So we need an equation that combines the things that we already know, maybe the thing that we learned as well, this final velocity, and what we're looking for, which is T. Okay, so all of the equations involve T except for number 6, but that's okay because we just use number 6. Okay. So if we look at these equations, 3, 4, and 5 might be great options to use, right? Because we have the velocities, we have the change in position, we have acceleration. My recommendation is to just
I would say 4,
list.
maybe.
You could do 4.
Because four, we found our final velocity.
Mhm.
So all we need to do is isolate t and it would work, right?
Right. Yeah, so
Okay.
I chose equation 3 just because it looks the simplest to me. And why complicate things if you don't have to?
Oh,
But
whoops. Yeah, let's go 3.
but number 4 would also be a totally acceptable choice and should give you the same final answer. Same thing with 5, right? It should give you the same final answer. It's just a little bit more complicated because there's that square on the t term there. So we'd have to use the quadratic equation, which you'll probably have to do at some point anyway. But not right now, because there's a simpler one. Right, so we plug in our final velocity that we just found in part A, our initial velocity of 0, and our acceleration, and we get a time of 3.46 seconds. Now, part C, calculate the average velocity. Well, there's one equation that explicitly states average velocity. So let's use that one. That's the change in position over the change in time. Well, we know what the change in position is from part A. We just calculated the change in time because we're going to assume that we'll start the stopwatch like as soon as the car starts moving. So initial time is 0, final time is 3.46 seconds. That gives us a change in time of 3.46 seconds. That's our time interval. So that will give us an average velocity of 8.67 meters per second.
Question.
Sure.
I thought that delta t would mean the change in time.
It
Oh
does.
wait, hold on. Oh, okay. That was a dumb question. Because you had change in x is 30 meters. I thought it was like some interval or something.
It is an interval. Yeah, that's absolutely right. I didn't explicitly write it down like on this slide, but we're assuming that our time starts from 0 and that our position starts at 0. And so that's kind of that idea of like setting up our coordinate system, our frame of reference, wherever it's most convenient. To me,
So
it's
would delta
convenient to
mean
set it
our
at 0.
final in
Would-
like position or time?
Yeah, so this 30 meters, that's our final position, right? Because it's after it has traveled 30 meters. So if we're starting at the 0 point and it's traveled 30 meters, that means its final position is 30 meters. But 30 minus 0 is still 30,
Okay,
right?
sounds good.
Okay.
What equations did we use for A again? Was it 6?
It was number 6 for part A. Yes, and you could have used 3, 4, or 5 for part B. I chose 3 because it was simplest. And then for part C, I chose equation 1. Now, there's a question in the chat. Will rounding up the decimal matter as the final answer? That depends on your professor. How many, like if significant figures are important to them, then rounding is generally not. I mean, you want to round to however many significant figures matters to them. Now, if you're in the middle of the problem and you're going to use that number for a later part of the problem, my recommendation to you is to not round to the nearest whole number, just because rounding in the middle will kind of carry down into later steps of the problem. So I typically use like 3 sig figs as my rule of thumb throughout a calculation. And then maybe I'd round my absolute final answer if I had to. But typically I just leave it at 3 sig figs. Okay. Any other questions about this example? Cool. Woohoo. Okay. So free fall acceleration. The most familiar example that we have of motion that has a nearly constant acceleration is just an object falling down. So when it's falling down, it's under the influence of Earth's gravity, right? And so the Earth, since it's massive, it generates a force of gravity. And so the Earth is pulling down on everything. and that is causing these objects to fall down towards the earth, right? So I say this acceleration is nearly constant because it does depend on your distance away from the earth. And so like things like altitude makes a little bit of difference in our acceleration due to gravity. So for example, down here in Melbourne, since we're practically at sea level, then our acceleration due to gravity was measured by the Coast Guard to be 9.792 meters per second squared. Hold on just a second. My baby is crying. Okay. So down here in Melbourne, Florida, it's 9.792 meters per second squared. If you took physics in high school, you might have rounded that up to 9.8 or 9.81. Again, it really depends on your altitude, how far away from the surface, well, from the center of the earth you are.
Wait, I'm a little bit confused.
Sure.
Ooh, what was the number of acceleration due to gravity in Melbourne?
9.792.
9.792.
We're gonna be representing it as like 9.8, right?
Yeah, generally.
Yeah,
Yeah.
that's
The
the
average.
thing you actually gotta remember.
Okay. So there were a lot of like misconceptions about gravity previously. So in the 4th century, Aristotle thought that heavy objects fall faster than lighter objects, proportionally to their weight. And that was thought for a really long time, but was actually proven incorrect later on in Galileo's, famous experiments. So he argued that an object should fall with a constant acceleration regardless of the weight if we can ignore air resistance. So really it's the air resistance on the object itself that makes objects appear like they are falling under different accelerations.
Yeah. Just to add something, sorry.
Yeah, go ahead.
I saw this documentary where they dropped a feather and a bowling ball in a vacuum, and they followed at the same speeds.
You
Yeah.
saw
That's
that
because there
one
was
too?
that's because there was no air resistance. So
Ah.
it allowed them to fall at the same speeds.
Yeah, and then they did that same sort of experiment on the moon as well with a feather and a hammer, right? And they hit the surface of the moon at the same time. So yeah, it's really just due to the air resistance that objects don't fall, all together all the time. So when we refer to something being in free fall, we're really just referring to something that's falling, or rising and then falling due to just gravity itself, ignoring any other forces like air resistance. Air resistance, of course, like is a real thing that you have to deal with if you're an engineer and all that jazz. But just for the sake of simplifying our calculations for now, we will pretend air resistance is not a thing. So no outside forces acting on you or the object except for gravity. That's what we mean when we talk about free fall. So comment in the chat. Air resistance is basically like the friction of the air. Yes, absolutely. It's friction due to air.
How does one measure air resistance?
I actually do have a slide on air resistance later on, so we'll get back to that question. And then there's another question in the chat. How does terminal velocity work? I will actually talk about that in just a moment as well. Man, you guys are like so just on top of things.
Terminal velocity is when the air resistance doesn't let you speed up anymore.
Right. So in that case, we do need to consider air resistance when we're talking about terminal velocity. But for now, since we're just doing free fall, we're going to ignore air resistance. Okay. So acceleration due to gravity is a very, very important concept in Physics 1. And so it's so important that we have given it its own special symbol, and that's lowercase g. So whenever we're talking about the acceleration due to gravity, we will always see it written as lowercase g, not capital G. That is something completely different. Lowercase g. And
Capital G is the gravitational constant.
yes. And our average value, like I said, it depends on your elevation, but our average value that we typically use is 9.8 meters per second squared. Right, so that would be close to the surface of the Earth, wherever we're doing our experiments for our purposes. The acceleration due to gravity is 9.8 meters per second squared. Now on the moon, since the moon is much less massive, it has a much smaller acceleration due to gravity. So that would be 1.6 meters per second squared. But since the sun, for example, is super massive compared to the Earth, it has a much larger acceleration due to gravity. So it's kind of pulling on things stronger to make them speed up more. And that is 270 meters per second squared. So there's a question here. Does it make a difference if G is negative? And that is a really excellent question. I'm very glad you asked that. Remember, negative implies a direction. So if we say negative 9.8 meters per second squared, that means that it is pulling down, right? Because down is one of our negative directions. And that should, make sense just conceptually. Like the Earth doesn't naturally propel things up because of gravity. It pulls things down. And so a lot of times we will use it as a negative number, right? But it does depend on your coordinate system, whatever is most convenient, as long as you keep it consistent. Yes, there's a question.
So like, you know how there's an equation for when there's two objects that have a gravitational force?
Yep.
Like pulling on each other. So would the gravitational force ever be like negative in any of those cases? I mean, not negative, positive.
Again, it depends on your definition of coordinate system. So you can define a coordinate system to say like towards me is positive. And so if because I have gravity as well, since I have mass, right? So something that is gravitationally attracted towards me, you could say, oh, that's a positive force then, because towards me is positive. But you could just as easily define it the other way as well. So it really just depends on your scenario. Pulley system. Interesting. Okay, so this bullet point is kind of what we were just talking about, right? G itself is the magnitude of the vector quantity. So that 9.8 meters per second squared that we have written up here, that's just the magnitude of it. So the magnitude is positive, but that direction, depending on your coordinate system, will make it either positive or negative. Okay. So looking at this last bullet point here, this white one, a ball thrown upwards will travel upwards, but while it is traveling upwards, it is accelerating downwards, which just kind of feels like a bizarre thing to say, like, oh yeah, it's traveling up, but it's accelerating downwards. Like, it just feels.
But that downwards acceleration is making it stop speeding up upwards and eventually fall down.
Yes, and that is an important thing, because if that didn't happen, then anytime you jump into the air, you'd just be gone, right? So we need that acceleration due to gravity to be downwards, accelerating us downwards. Otherwise, that would just be a very, very bad day.
You could call it deceleration.
Hmm?
You could call it deceleration.
You could call it deceleration. Typically, we don't use that word in physics just because it would be logical. I don't know. Sometimes we don't do logical things in physics. We just have acceleration and positive and negative acceleration, and yeah. All right, so here is our free fall example, example 2. A coin is dropped from the Leaning Tower of Pisa. It starts from rest and falls freely. What is its position and velocity after 1 second, 2 seconds, and 3 seconds? Okay, now just for the sake of time, I have included a sketch of the scenario. Typically though, this is something that you would want to make sure you do yourself, draw out the scenario. Did you guys see some of those important key phrases to notice in the problem statement? From rest, falls freely. Those are important. It's dropped. It is not thrown. It is dropped. Okay. So dropped itself implies that it starts from rest, right? So the problem wouldn't have had to explicitly state that either. So look for those keywords. Get used to kind of hunting those out. So that means
If
it's
it was
initial-
thrown, then you have to include some sort of some like positive units in there, then like take it out with the minus.
Well, if it's thrown, it depends how it's thrown, but if it's thrown, then it's given an initial velocity that is not 0.
Yes.
To take that into account in your calculation. Yeah. Okay, so initial velocity is 0. It's falling freely, meaning that we are ignoring air resistance. And the acceleration is 9.8 meters per second squared downward. Okay, so we didn't need to explicitly give you a number for initial velocity or acceleration. They're both secretly embedded into the problem statement. Okay, now we want to find its position and its velocity after these different time intervals. So you can see we have given you time values as well. Okay. All right. So if you have like access, if you wrote down those equations that we went through in the previous example, those would be helpful to be able to refer back to. Just for the sake of time, I just gave you which equation would be most helpful to use in this case. And you can see we now have the variable y where previously we had x. And that's just because now we're dealing with motion vertically as opposed to horizontally, right? So when we had our car example, it was driving horizontally, so we used x. But now this coin is falling vertically. So anywhere we see x, we're going to replace it with y instead. Right, so x became y. Our initial velocity is now an initial velocity in the y direction. So v0y is another way we can write that. Remember, previously we used vi. Here I'm just showing you a different notation. That's all. Okay. So some things that we know or can assume that we can start plugging into our equation would be an initial height of 0. Now that might seem like a really strange choice to use, right? Our initial height is 0. Why wouldn't you make the ground a height of 0? Absolutely, you can do that. However, we don't know the height that you are dropping this coin from. And so if we choose our coordinate system so that 0 is where we're dropping it from, then we don't even have to worry about that, right? We can find its position later as we're asked to do that. Okay, so choose a coordinate system that makes it most convenient. 0 doesn't have to be at the ground. Okay, so if we say our initial position is 0, it's dropped from rest, so initial velocity is 0. It's falling freely, so its acceleration is g, and it's falling downward, right? So that's a negative. Now we've just taken our kind of complicated looking equation and simplified it quite a bit. So now we're just dealing with this equation here, negative 4.9 t squared is our equation. Okay, so a similar process when we want to find the velocity after a certain time, right? I'm going to use this equation for velocity. This is equation number 3. This one was equation number 5. Just because this is simple to look at, right? So our initial velocity was 0. Our acceleration was negative g, and time we have as well. Okay. So we can just plug in our values for time, right? So if time is 1 at 1 second, then we just have negative 4.9 times 1 squared, which is negative 4.9 meters. So it has fallen down a distance of 4.9 meters. The velocity at that point is negative 9.8 times 1. So velocity is negative 9.8 meters per second. Again, that negative tells us that it is traveling downward. You can do the same thing for 2 seconds. We just plug in t equals 2, and we'll see that we have a position of negative 19.6 meters, right? Negative again, because our initial height is 0 and it's falling downward. So a negative position. And then a negative velocity of 19.6 meters per second. Same thing for the third part, just plug in t equals 3 and you get your answers there. Okay, any questions about this example? Go ahead.
Oh, I think I'm good.
Okay. Well, let me see what is next.
Oh, wait, can you go back?
Sure. Let me know when you're ready.
I do have one question.
Okay.
How come in the second line for the equation,
Mhm.
it's negative 4.9?
Because 1/2 of g, remember g is 9.
Oh, okay.
Yes.
Well, thank you.
You're welcome.
I'm ready.
Okay. So I think we should have enough time to get through example 3 as well, and then this will be the last thing that we do today. So example 3, you throw a ball vertically upward from the roof of a tall building. The ball leaves your hand at a point even with the roof railing with an upward speed of 15 meters per second. Then it is in free fall. On its way back down, it just misses the railing. Okay, so there's a lot to unpack here in this problem statement. Okay, so now we're throwing the ball, we are not dropping it, so our initial velocity is no longer 0. Okay. We have an initial velocity of 15.
15.0.
Yes, 15.0 meters per second. Positive because we're throwing it upward. Okay. Then after that, it's in free fall. So again, we're not dealing with air resistance. Our acceleration is due to gravity. So that's 9.8 meters per second squared. Okay, so here's our very official sketch of the problem. So we'll say time starts right here where we let go of the ball. And we want to know in part A, the position and velocity of the ball 1 second and 4 seconds after it leaves our hand. Okay, so I'm using the same equations that I did in the previous example. It's just that now our initial velocity is not 0 anymore, it's 15. But we can still define our coordinate system so that 0 is where I'm letting go of the ball, where I'm throwing it from. So we can still have an initial position of 0, even though our initial velocity is not 0 anymore. Okay, but it's the same process that we did in example 2, just with this extra chunk now of 15 times t in our equation. Right, so 15t plus 1/2 times negative 9.8 times t squared. That will give you your positions once you plug in your time interval. So 1 second and 4 seconds. And then our velocity equation is the same as it was in example 2, but again, we have an initial velocity of 15 now. So once we go ahead and plug in our values for t of 1 and 4, we'll get our answers for our positions and our velocities. Now, if you take a look at our positions, right, at 1 second, we're at a position of 10 meters. So again, that's 10 meters from our hand. But at 4 seconds, we're at a position of negative 18 meters. So at 18.4. So at some point between 1 second and 4 seconds, this ball reached the top of its peak and started traveling back down past the railing by 18.4 meters. Okay, and we can know that too. We can verify that from our velocities because our first velocity is positive 5.2 meters per second. And our second velocity answer is negative 24.2 meters per second. So the fact that the first one is positive and the second one is negative means that at some point within that time interval, it has changed direction. Okay, so I'm going to stop here for now just because I think there are several other parts to this example and I don't want to keep you too late past 4:30. But we'll pick up here tomorrow. We'll finish out this example and then we'll continue on. Do you guys have any questions about this part A before we wrap up?
Yes.
Okay, go ahead.
I'm looking at velocity in the not in the vertical direction,
Mhm.
and it says plus 0.5. No, sorry, plus 5.2. What does that like? How do I find that?
So I used this equation right here
Uh,
to find our velocity. And since our initial velocity was 15, right, we threw it upward with 15 meters per second. Our acceleration, since it's in free fall, is negative 9.8 meters per second squared. And then that time is 1 second for that part. So 15 plus negative 9.8 gives us a velocity of positive 5.2 meters per second. I'm sorry, meters per second. Question,
okay.
do we meet on Friday or finish the equation on Monday? We do not meet together tomorrow. Remember, tomorrow is an enrichment session, which it's optional. You're welcome to go or not go. It's up to you. So we'll finish out this example on Monday then, and continue talking about motion in. Oh, you're right. Thank you. It is Tuesday because Monday is the 4th of July. Thank you so much for reminding me. I would have completely forgotten to mention that. Monday is the 4th of July. So the next class will be on Tuesday. So we have a nice long break to ponder what else I can ask you about this example. Yes, so no class tomorrow because of the enrichment session. No class on Monday because of the 4th of July. We'll be back here on Tuesday. Well, I hope you guys have a great weekend. Enjoy the super extended weekend. Happy 4th of July to everybody. And I will see you Tuesday.
Yeah, this
Oh.
is amazing because I remember this question on one of my exams. I failed that exam, by the way.
Oh no.
Now I understand it, which is very telling about the quality of my education like 6 months ago.
Well, I'm glad you understand it better now. That makes me happy for you.
I got one question. On the day that you were having connection troubles,
Yes.
is this the continuation of that day? Or
No, so there was a day in between because that was on Tuesday. And so yesterday I was sick. And so I posted the continuation of that on Canvas for you to watch.
okay.
Hey, you're fine. It's okay. He's not thrilled about learning physics, apparently.
Have a wonderful weekend.
Thank you.
Thanks, you too. Have a great
Have a nice weekend.
Bye.
Bye. Have a good weekend.